Hi Wayne, hi Travis. This is John Whitaker for the Probability Graduate Level class, and this is our 18th video lecture. And today we're going to start Chapter 3, which has to do with conditional expectations, conditional probability mass functions, conditional probability density functions, and we're going to be in this chapter conditioning on things. And so let's go ahead and get started by me indicating that this is Chapter 3. And just as a quick reminder, this is the first video for what will be the material covered on Test 2. Okay, so Chapter 3, what we're going to start off with is the definition. And it says, let x and y be two discrete random variables then the conditional probability mass function of x given y is denoted by, okay, we write down little f, x given y, big X bar y, of little x bar little y, so x given y, and is defined by so here it is, f of x given y of x given y, what is equal to is f of x comma y over f sub y of y. And here, where f of x comma y is the joint Pmf of x and y, and f sub y of y is the probability mass function of y. And of course this is defined for y values where f sub y of y is greater than 0. Write that down. For which f sub y of y is greater than 0. If we have the definition of the conditional probability mass function of x given y, we can similarly define the conditional probability mass function of y given x is f sub y given x, y bar x, which is equal to f of x comma y, the joint Pmf of x and y, over f sub x. And the idea is very easy to see. That is, f sub x given y of x given y, what that's going to be equal to is the probability that x is equal to little x given y is equal to little y. That's what the conditional probability mass function is. And of course, how would we define this? Well, we have a conditional probability that we're being asked to do, and we know that that's the probability of intersection, comma, meaning the intersection, which over the probability that y is equal to y. And so that is equal to, if you know the joint PMF, it's f of x comma y, and then the bottom is nothing more, the probability that y is equal to root of y, is nothing more than the PMF of y evaluated at y. And so that's how we get the definition, that's what motivates the definition. It's this idea that the conditional probability mass function gives you the probability that x equals to x, and given that y equals to y. Let's look at an example next. We'll look at that similar example, we looked at many times before. So here, we'll let f of x comma y be equal to x plus y over 21, where x is equal to 1, 2, and y equals to 1, 2, and 3, be the joint PMF for the discrete random variables x and y. Okay, and here the questions will be two parts. So find, part A is the conditional probability mass function of f of x given y. So we know what that is. And B, find the conditional probability mass function of y given x of y given x equal to 2. Okay, so that's what we'll do. Let me start with part A right here. So here's the thing that I know. By definition, this conditional probability mass function of x given y is equal to f of x comma y over f sub y of y, the PMF of y. And so I already have f of x comma y, the joint PMF. What I don't have is the PMF of y, so that's what I need to work on. So note f sub y of y. So this is the, as I said, the PMF of y. And the way that we get it from the joint PMF is that we would say that's the sum over all x values, well, the x values are from 1 to 2, of f of x comma y. And so what that would be equal to is f of 1y plus f of 2y. And so what is that? Well, f of 1 comma y is 1 plus y over 21 plus, here would be 2 plus y over 21. So I'm going to be getting 3 plus 2y over 21. So the conditional PMF of x given y is going to be equal to, let me remind you, f of x comma y over f sub y of y, which will be equal to, well, this is defined in our problem. So that's x plus y over 21. And we divide that by what we just found, which was 3 plus 2y over 21. And so when you do that division of those rational expressions, we get x plus y over 3 plus 2y. That's my answer for the conditional probability mass function of x given y. Again, x is equal to 1 and 2. Y equals to 1, 2, and 3. Well, let's handle part B of the problem. So for part B, let us recall what it is we're looking for. So part B, f sub y given x of y given 2, what that's going to be equal to is f of, well, it'll be x comma y, but here we know x is 2, so it's 2 comma y, over f sub x of 2. That's what I got to find. Well, this is equal to, so this was, remember this, in general, f of x comma y was x plus y over 21. So here's going to be 2 plus y over 21, all divided by the probability mass function of x evaluated at 2. Well, in general, f of x, the probability mass function of x, is the sum over all y values, that's 1 through 3, of f of x comma y, which is going to be equal to f of x comma 1 plus f of x comma 2 plus f of x comma 3. And then that's equal to what would be x plus y is what it was, so that's 1 in this case over 21, plus x plus 2 over 21, plus x plus 3 over 21. When you add those together, you get 3x plus 6 over 21. Of course, 3 can be factored out. So you end up getting x plus 2 over 7. Well, let's just leave it as 3x plus 6 over 21. So f sub x of 2, well, what that's going to be equal to is going to be 3 times 2, that's 6, plus 6, that's 12 over 21. Thus, the conditional probability mass function of y given x, y2, is equal to 2 plus y over 21, that's where I'm looking, all over 12 over 21. That ends up being 2 plus y over 12. Whoops. And so that's what we get for this answer. Okay. All right. So here's another definition. Or you can think of it as a fact, but it says, let x and y be discrete random variables. Then, so I'm defining this probability. Probability that x is an element of A given that y equals to y is equal to the sum over all x values in A such that f of x is greater than 0 of f, so x given y of x given y. That's what it is. We'll do an example of that in a minute, but that's the definition for the probability that x is in A and given y is equal to y. Another thing we want to talk about is the conditional cumulative distribution function. So, if we let x and y be discrete random variables, then the conditional cumulative distribution function of x given y, let's say how it's denoted, is denoted by big F of x given y of A given y. We'll write it down this way, of A given y equal to y. Which is defined to be the probability that x is less than or equal to A, given y equals to y. And by our previous definition, this is the sum over all x values less than or equal to A of f of x given y of x given y. Okay, and of course we're only summing these up for where the f of x is greater than 0. So that's what we have. And so let's look at an example. So let's let x and y be discrete random variables. With joint PMF, f of x comma y is equal to 2x squared plus 3y over 182 with x equals 1, 2, and 3, and y equaling 1, 2, 3, and 4. And so we'll have two parts to this. Part A is find the conditional CDF, cumulative distribution function, of x given y. And part Part B is find the probability x is greater than 1 given y equals to 3. Okay, so for Part A, so I'm looking for the conditional CDF of x given y. It's f of x given y of a given y, y given y. And so we want to know what the chance x is less than or equal to a, given y is whatever it is. And what we'll do here is first notice that there are several cases because of what x's values are. And so here, we'll say it this way. We'll say, note, case 1, if a is less than, so the smallest x value that we can have is 1. So if a is less than 1, then f, so x given y, of a of y given y equals y, that's going to be 0. No way that that's going to be a positive number because x is always 1, 2, or 3. Now, case 2, if 1 is less than or equal to a less than 2, then f of x given y of a of y equals y. Well, this was the sum over the x values that are less than or equal to a. So this would just be the sum as x equals to 1, so just one thing, 1 to 1, of f of x given y of x given y. Okay? And I don't have that, so I need to compute that. Well, note, f of x given y of x given y is going to be equal to f of x comma y over f sub y of y, and f sub y of y is the sum over the x values, x running from 1 to 3, is what the x values can run from, of f of x comma y. And so I'll finish that up over here. Don't forget, I have to find it. I'm going to leave half the board here unerased so we can see the example still. So here, this is equal to, remember, I'm computing f sub y of y. So, okay, so here's where x is equal to 1. So, I'm sorry, so I sum from x equal 1 to 3, as I said over there. So when x is 1, we're going to get 1 squared, that's 1, times 2, that's 2, plus 3y over 182, plus when x is 2, we're going to get 4, 8 plus 3y over 182, plus when x is 3, we're going to get 9 times 2 is 18 plus 3y over 182. And so, what is that equal to? Well, it's 10 is 28 plus 9y over 182. Okay, so f of x given y, I need that, of x given y is going to be equal to, well, it's this quantity right here, which is 2x squared plus 3y over 182, all divided by, there's 28 plus 9y all over 182. And so that ends up being 2x squared plus 3y over 28 plus 9y. Okay, and so the conditional CDF of x given y here of a given y equal to y, where I'll say equals. The sum is x runs from 1 to 1 of this quantity, so it's 2x squared plus 3y over 28 plus 9y, and here I'm just letting x be 1, so this ends up being 2 plus 3y over 28 plus 9y with, in this case, that was 1 is less than or equal to 8 is less than 2. Now, case 3, because of what the x values can run from, 1, 2, and 3, we consider A being sandwiched in between 2 and 3. And then F, the conditional CDF of x given y, evaluated A, y equal to y. That's going to be the sum. So A is between 2 and 3. So when we think of the x values that are less than or equal to 8, that means that it could be equal to 1 or 2 of the conditional probability mass function. So that's going to be 2x squared plus 3y over 28 plus 9y. And so here are two things added together. When x is 1, again, I get 2 plus 3y over 28 plus 9y. And then plus, when x is 2, this is going to be 4, it's going to be 8 plus 3y over 28 plus 9y. So we end up getting here, that's going to be 10 plus 6y over 28 plus 9y. So that's what the conditional cumulative distribution function is when A is sandwiched between 2 and 3. And then the last case is when A is bigger than 3. Well, bigger than or equal to 3. So this conditional CDF, it's going to be the sum as x runs from 1 to 3 of the conditional Pmf of x given y. So the sum as x runs from 1 to 3 of 2x squared plus 3y over 28 plus 9y. And let's see what that is. That's going to be 2 times 1 squared, that's 2, plus 3y over 28 plus 9y. Plus, when we have x equal to 2, we're going to get 4 times 2, that's 8, plus 3y over 28 plus 9y. Plus, when x equal to 3, we get 18 plus 3y over 28 plus 9y. And that is equal to 28 plus 9y over 28 plus 9y, and that's equal to 1. And that's what we would expect. Now, for part B, we wanted to calculate the probability x is greater than 1, given y is equal to y, well, y was equal to 3. And what that was defined to be, our definition on this side of the board here, before we did the conditional CDF, is this is going to be equal to the sum over all x values bigger than 1 of f of x given y. But we know y is 3, so I'll write a little 3 here. And so that's equal to the sum as x is equal to 2 to 3 of f of x given y of x3. And that's equal to the sum at x runs from 2 to 3 of that conditional Pmf was 2x squared plus 3y over 28 plus 9y. Except we know what y was. Y is, they said 3, so I substitute in for y 3. And so here, when x is 2, we're going to get 8 plus 9 over, so this is 27, I think this is 55, plus, when x is 3, this is 18 plus 9 over 55. And so that's 17 plus 27 over 55, and that's 44 over 55. And you notice we're talking about probability, and the answer here is between 0 and 1. That's a good sign. Okay, so that concludes the example. The next thing I want to do is give a definition. So here, we're going to let x and y, instead of being discrete, be jointly continuous. So let x and y be jointly continuous random variables. With joint PDF probability density function f of x comma y. Okay. Then the conditional probability density function of x given y. Well, it's defined similarly and denoted similarly to discrete cases. F sub x given y of x given y, little x given little y here, is defined by, okay, so f of x given y of x given y is equal to the same thing. F of x given y over f sub y of y, where that's the joint PDF over the PDF of y, the given part. Okay, similarly, the conditional PDF of x, of y given x. Really, I shouldn't have to define this, but it's the same. Okay, one variable given the other. Is f sub x, f sub y given x of y given x is equal to f of x comma y over f sub x of x. Let's look at an example. Well, let's let f of x comma y be defined by 12x if 0 is less than y is less than 2x is less than 1, and 0 otherwise. B, the joint PDF of x and y all right, then what we're going to do is find, for part A, 2 parts, the conditional PDF of y given x, and part B, we'll find the conditional PDF of x given y both of those. Well, because we're talking about continuous random variables here, we're going to be integrating instead of summing. So here, the conditional probability density function of y given x, by definition, joint PDF over the PDF of x. Well, let me write this down. This is equal to, so I have the top part. Well, it's 0 a lot of places, okay? So here it's, let me write it down this way. F sub x of x, what's it equal to? It's equal to the integral from minus infinity to infinity of the joint PDF d1. Now, by the way that the joint PDF was defined, the region where we're integrating, so it says if 0 is less than y, is less than 2x, is less than 1. So here, y runs from 0 to 1. And 2x is in between 0 and 1, so that means that x itself is between 0 and a half. So I'm looking at this square, and then y equal to 2x is this diagonal line. And we want y to be less than 2x, okay? So here, let me try a point. How about this point right here being 0.1, so 0.19, is that satisfied that the y value is less than twice the x value? No. But what if I take a look at this point, which I'll say is 0.49, and then 0.1, and is that satisfied? Yes. So it's this region that I'm integrating over where the joint PDF is non-zero. So this then changes my bounds for integration. So for a fixed y, okay, so here, for a fixed y, we have, first of all, what we're integrating is 12x, okay, and the y values can run from 0 to 1. Right, so that's what the y values run from, 0 to 1. You know, really, the y values here run from 0 up to the x value. That's what they run from. That's what they run from. And I've got 12x. That's what it should write. And so this is dy. Okay? I made a mistake. So for fixed x value, that's what they run from. And what is my answer here? Well, the antiderivative is 12x with respect to y. Evaluated from 0 to x. That's what the y values are. that's going to be equal to 12xx minus 0, which is 12x squared. Okay. That's what I have. Give me a second, I want to make sure I'm not making a mistake. For fixed x, that's what the exact run from. I have with respect to y, that's what I get. Okay. So, f of y given x is equal to, here, what that was defined to be was 12x over, this is 12x squared, and so I just get 1 over x. And this is for x values in between 0 to a half. That's part A. For part B, and we're finding f sub x of y, x given y. And what that's defined to be is f of x comma y over f sub y of y. So again, we've got the same picture here. So to find f sub y of y, that's the integral over the x values. So here, dx of minus infinity to infinity of f of x comma y, which is equal to, well, for a fixed y value, here's where we're looking. Y is less than 2x. The integral from, it would be from, so for a fixed y, the y values run from 0 to 1. But for a fixed y, the x values run from this line. I made a mistake. I knew I was making a mistake. I'm sorry. Let's go back here. I knew I was doing something wrong. Please forgive me. I was thinking this line was y equal to x. It's not. This line is y equal to 2x. So here, this should have been a 2x. Make that change. So here's a 2x. It didn't match my notes, but I couldn't figure out what I was doing wrong. So these are y values. So here, I put in 2x for y, and I have 24x squared. So right here, this should be 2x. And so here, I get 24x squared, and that's 1 over 2x, again, where 0 is in between, I'm sorry, x is in between 0 and a half. That's correct. Make that change. I'm sorry. Again, my mistake here was I thought this line was y equal to x, but it's not. It's y equal to 2x. Yeah. Okay. So here, this line is y equal to 2x. We're integrating this over this lower half. And so for a fixed y, the x values run from here to there. So this has x is equal to y over 2. So the lower x values is y over 2, and the upper x value is a half. And this is going to be, remember, 12x. So here it is dx. So that's equal to 12x squared over 2, evaluated from y divided by 2 up to a half. So this is 6x squared, evaluated from 1/2 to y divided by 2. Okay, so when I stick in 1/2, what I get is 6/4 minus And this will be 6y squared over 4. So that ends up being 3/2 times 1 minus y squared. That's what I get for the PDF of y. Yes, that's right. So the conditional PDF of x given y is going to be 12x over, here it is 3 halves times 1 minus y squared. That's what it is. And that's what I got. And so that's the same thing, if you will, as 8x over 1 minus y squared. Okay, so that's what we computed. There are some restrictions here, what x and y can be. They have to be in that right region. Here, 0 is less than, I think y is less than, 2x is less than, I think it's 1. That's what we had, something like that. It was whatever was involved in the definition of the joint PDF. That's the restrictions I need there. Otherwise, it's 0. Okay, so a definition is that if we let x and y be continuous random variables, then the probability that x is an element of A given y equals to y is equal to the integral over A of f of x given y, then we're integrating with respect to x. That's its definition. And as an example, we let u and v be continuous random variables with joint PDF f of u comma v equal to, well, it's 1/2 uv, and that's what it is, if 0 is less than u is less than v is less than 2, and 0 otherwise. Then the problem says find the probability u is less than 1/2 given v equals to 1. Okay. So to do this, what we need to know is that f of u given v, is equal to f of uv over f of v. F sub v of v. Okay, well, we have this given to us, the joint PDF, but I don't have the PDF of v. So note, f sub v of v, well, it's going to be equal to the integral from minus infinity to infinity of f of uv with integrate with respect to u. So let's think about the region that I'm integrating over for the joint PDF. Okay, this is the u-axis, there's the v-axis, and what we have is both of them run from 0 to 2. We have u equal to v. We got v is bigger, it's this top part. Okay, that's what we find. And so for a fixed v, the integral becomes the u values will run from 0 to v. And this was defined, I have it over here, 1/2 uv du, which is equal to 1/4 u squared v, and here u runs from 0 to v. So I end up getting 1/4 u to the third. Okay, and we put in 0, you get nothing. Okay. So, I'm sorry, but this would be v to the third. Remember, we're letting u be equal to v. So it's v to the third. And so, f sub v of 1, which is what I'm going to need, is going to be equal to 1/4. Now, thus, f sub u given v of u given v equal to 1 is going to be equal to f of u1 over f sub v1, and f of u1 right over there is going to be 1/2 u from the joint PDF over, here's 1/4, so it ends up being 2u. Okay, so from our definition, this probability that, remember what we're looking for, that u was less than 1/2, that's given v equals to 1, that's what I'm writing the problem is. Okay, so we integrate over u being less than 1/2 of this conditional probability density function, which we found to be 2u, okay, du. But this region, u being less than 1/2, the u values, okay, in this case, are from 0 to 1/2 over the region that we're looking at. So let me write that down. Here's what we're looking at. And so we have u is equal to 1/2, right? And so so u is less than 1/2, okay? So u is less than 1/2 is here. Okay? U is less than 1/2. So we're integrating over this region. So that region is the integral, and we know v is equal to 1. So really it's like this line integral here. So here's what we have. We have from 0 to 1/2. Okay? So v is equal to 1. So for v equal to 1, just over this region, here's what I think of. The u values run from 0 to 1/2. Okay? So it's over that line of 2u du. That ends up being 2u squared divided by 2, evaluated from 0 to 1/2. That ends up being 1/2 squared, which is 1/4. So what I did here was I fixed that v was equal to 1. I'm just looking at this part, v is equal to 1, and I'm saying over that region, what does the u run from? And the u runs from 0 to 1/2. That's how I got this limits of integration. Okay, here's a fact. if x and y are independent, then the conditional probability density, the conditional PMF or PDF of x given y is equal to the PMF or PDF of x. And so the proof is real simple. It's one-line proof. So the one-line proof is the following. It is, note, f of x given y, by definition, is f of x comma y over f sub y. But if x and y are independent, we've already shown that this f of x comma y is equal to f of x times f of y, and then that's over f of y, and that's equal to f of x. So that's the proof, real simple. Okay, there's only one more concept for this lecture, and then we're done. So the last concept is that of a conditional expectation. All right, so here we're going to let x and y be discrete random variables. Then the conditional expectation of x given y is denoted by the expected value of x given y equal to y, and defined by the expected value of x given y equal to y. What's it going to be is it's the sum over all x values such that f of x is greater than 0 of x times the conditional PMF of x given y. And so let us look at one example and then call it quits. So the last example is, let f of x comma y be equal to our old example, x plus y is 21. If x is equal to 1 and 2, and y is equal to 1, 2, and 3. And so here's what I'm asked to find. Find the expected value of x given y. Okay? And so here's what I say. Well, by definition, the expected value of x given y is equal to the sum as x runs from 1 to 2 of x f of x given y. X given y. I think that I had already found this, so I'm going to go back in my notes and tell you what that is. So f of x given y, I think, is the sum as x runs from 1 to 2. We had done this before. I think it's x plus y over 3 plus 2y. I think that's what we had found. Okay. And that's going to be equal to, so here, we're going to get 1 plus y over 3 plus 2y plus, it would be 2 plus y over 3 plus 2y, and that's equal to 3 plus 2y over, okay, so wait a second. Oh, I forgot the x. So here, there should be an x. So here should be a 1, and here should be a 2. So here, this ends up being 1 plus 4, that's 5, plus 1y plus 2y, that's 3y, over 3 plus 2y. That's right. Okay, that's the right answer. And what I want you to notice is this expected value of x given y, really it's a function, or outputs function, it depends on y. We think of it as a random variable of y. Okay? That's what we think of it. So, just very quickly, I'll say the expected value of x given y equal to 1, just by letting y equal to 1, is 8 over 5. The expected value of x given y equal to 2, well, that's going to be 6, it's going to be 11 over 7. And then finally, the expected value of x given y equals to 3. That's going to be 9, it's going to be 14 over 6 plus 3, that's 9. Okay? Those are our answers. All right, gentlemen, that's enough for this lecture. Thank you very much for your time and patience.